So to so today's lesson, we're going to talk about bagging, which is basically using bootstrap methods in order to develop mini regression trees and to use an ensemble of these models in order for prediction. So I know last night or at least in the Jupyter notebook, I have some classification versions of the same thing that we're going to do today. But today I'm going to use it to do a regression, so that you see both the ability of this bagging method to do both. In order to understand bagging, you have to really understand what bootstrapping is. And so that's what the first part of this lesson is all about, is to sort of describe what we mean by bootstrapping. And then tomorrow or the next class, we'll talk about how to use this thing, or how to use these ideas in order to decorrelate. So right now, I feel like bagging is going to give you a correlated model, like all the models that we're going to create are going to be correlated to each other, because if you have one real strong predictor variable, that one will be the one that you're going to use sort of all the time, regardless of how you spread it or how you bootstrap the data. But if we're able to, for next class, we're going to decouple that, I believe, a little bit easier, and we'll show what that is when we get to random forest. But today, let's talk about bagging with bootstrap. So in order to be able to understand this, you got to remember what the expected value, that it's a linear operator, and sort of how to do that. And so this is just a recall that you pull the A out of the expected value, and the expected value of a constant is just a constant. So in this case, X is our random variable, A is a constant, and B is a constant. The expected value of this linear combination is just A times the expected value of X plus B. If you were going to do the variance the same way, you have to remember that when you pull the constant out of the variance, that you square it, and then you take the variance of X, and then the variance of course, so the variance of a constant is just 0, right? So that just goes to 0, so we didn't even write it. So that's what it would be if we were doing the variance of this linear combination. All right, so with that being said, let's use an n random variable. So I have x1, x2, xn be independent random variables from a population, and this population has a mean of mu and a variance of sigma squared. And then further, let's let x bar, this capital X bar, be a random variable as well, and let it be defined as basically the average of all of the random variables that come from these n random variables. And so you can see just 1 over n times the sum of all the random variables, and let that also be random, right? Because it just sort of depends on what happens with these x's is what's going to happen with x bar. And the question is, well, what's the expected value and variance? We can know that by these sort of rules that we established up here, that you can simply take the expected value of this linear combination here. So 1 over n, all these e to the x's, all of these are mu's. Why? Because they all come from, each one of these expected value of x comes from expected value of x2, expected value of xn. They all come from a population with a mean of mu. So that's going to be mu, that's going to be mu, and so on and so forth. So I'm going to have n of these things, and n mu divided by n is just mu. Therefore, when we get down here, we'll talk about that. Therefore, x bar is a unbiased estimator for the parameter mu. And then we get the variance. So we want to find the variance of x bar. Do the same thing. When you pull the 1 over n out, you get 1 over n squared. And then these are all sigma squares. And then I'll have n sigma squares, right? Because there's n of these suckers in here. And then n sigma squared. So we end up with this being the variance of x bar. Okay. A couple notes about that, right? So the first one is that x bar is an unbiased estimator for the parameter mu, and this thing called sigma over square root of n. So if I take the square root of the variance of x bar, this is the standard error for the estimator x bar. So just understand that standard error is what we're going to use in order to figure out, well, how good is this estimate, right? So I have this estimate, this unbiased estimator x bar, and the question is, well, how good is it? The way that we want to, and what I mean by how good is it, is how close is it to the true value of mu. We don't technically know that, but we know this sigma over square root of n. If we can estimate that guy, then that'll give us an idea of how close we are, right? So if this thing is huge, then we know that it's not a great estimate, right? So in other words, it could be a whole bunch of possible numbers, a range, a very large range of numbers that it could possibly be. But if this thing is relatively small, meaning that maybe n is a really big number. You know, if n is a number, then this whole thing would be a small number. Then we know that maybe the estimate for x bar is should be kind of close to a mu. Again, it's random, so we don't technically know for sure. But when this number, the standard error is really small, we know that we feel like we got a really good estimate for x bar. Okay, so s squared is the sum, you know, this little formula here, and it's basically the unbiased estimator for sigma squared. So we know that we can get that as well. Here's a couple notes. So the first one is the unbiased estimator and the standard error for the estimator can be easily acquired from the data. So x bar being the unbiased estimator for mu, estimator for mu. I guess I should have put for unbiased estimator, and standard error for mu can be easily obtained from the data. The unbiased estimator for sigma squared can be easily obtained. However, its standard error is not easily available. So I don't know, when I calculate s squared is equal to this little business right here, I don't know how tight that is. I don't know if that's a really small window that s squared could be in, or if it's large. Because really what we need is an estimate for the standard error of this estimator, and we just don't have that. So what we do is we end up using this thing called bootstrapping algorithm. So we need a method to estimate any statistic theta hat along with its standard error, and the idea is that we can use bootstrap as one method of doing that. So what is the bootstrapping algorithm? What are we doing when we I mean, here's the reason why. Why do we need a bootstrapping algorithm? Because some of these statistics, there's not a theoretical way to find the standard error like we did before. So now what we want to do is use the data in order to try to figure out a good estimate for my standard error. So what does the bootstrapping algorithm do? Suppose we have n observations from the original sample. What you're going to do is sample n values with replacement, and then you got to sort of decide. Maybe we do it 1,000 times. Maybe b is equal to 1,000. So we're going to do this 1,000 times. I'm going to sample n values with replacement, meaning that some of the original observations may appear in the bootstrap sample once, more than once, or not at all. So sometimes you're going to have, and I'll show an example here in a second, but you're going to have to decide how many of these bootstrap samples you're going to do. And then what you do is you calculate and record the statistic for each one of these bootstrap samples, and then use the population of the bootstrap sample to find an estimate for theta hat, meaning you just average all of them. And then you find the standard error for theta hat, which means you just find the sample standard deviation of all those. So for example, down here, I give you like 1, 2, 3, 4, and 5. Say that's my, those are my observations. Again, I don't have a great deal of imagination when it comes to these things. So I just basically gave you 5 numbers. And we know x bar is 3, and we could also calculate s squared. But the problem is, I don't know how to estimate with the standard error for this s squared. That's the problem. That's what we don't know. We can find it as an estimate for the standard error for this value 3, this estimator of 3, on this true, whatever the true population, wherever these numbers are coming from. But I claim that there's no easy way. There might be a way using some kind of statistics, but there's no easy way. And I'm sure there's going to be statistics, you know, that you can think of that you might not be able to find a theoretical way to calculate the standard error. So this bootstrap method gives us a way of doing that. So what all you do is, just like it says up here, sample. So we're going to do this 1,000. So again, I chose 1,000. I'm going to sample n values with replacement. What does that mean? Well, I got a 2, right? So a 2 came from here, and then I didn't just take the 2 away and just leave me with 1, 3, 4, and 5. I sampled a 2, and then I sampled another 2, and then 4, 5, and 1. So that is an example of a bootstrap sample that has 2 2s and not a 3. So like I said above, sometimes you're going to have multiple values of some and not any of other ones, and then maybe one of some of the other ones. So in this case, we could calculate x bar. We could calculate x bar. Here's another bootstrap example. I could call that number 2. Number 3 could possibly look like this, and maybe the 1,000th one looks like this. And so the idea is that I can take x bar, x bar, x bar. I don't really care about x bar because I can already theoretically find a standard error for this. The one that we said we couldn't find is this S squared, right? So I could call this S1, S1 squared, S2 squared, S3 squared, and that just is the bootstrap sample. So that there's going to be some number there. We can calculate that. There's going to be some number there. We're going to calculate it, and so on and so forth. There's going to be 1,000 of these numbers. And now what happens is you might start getting, if I had 1,000 of these guys, maybe you could put a histogram, and it looks something like this, where now these are all my S squares. No, histogram of S squares. So maybe this is maybe 2, 3, 4, 5, 6, 7, 8. I don't know. Again, I haven't calculated any of these. I don't know what they are, but maybe they look something like this. And this is the frequency. So this is the frequency of S squared, right? So maybe it looks like this, and we can actually calculate the mean of all these. So again, up here where it says estimate theta hat, so I could estimate S squared by finding the mean of these 1,000 S squares. Mean of 1,000 S squares. And then, so that we could do that. And then maybe the standard error, so the standard error of S squared is the standard deviation. So find the standard deviation of the 1,000 S squared. And so that's what we would do in order to get that estimate. Okay. So what does that allow us to do? It allows us to then bring down, if we want, I can bring down the standard error by increasing, 1,001, 1,002, and so on and so forth. We could just keep doing this over and over again until we could bring down the variance of my estimator. Now, I think I said earlier that the idea of bagging is to use this idea of bootstrapping in order to calculate a whole bunch of models. So what does that mean? Well, we'll come back here in a second. So we're going to go back to we're going to go to the code, and we're going to see what's going on, and I'm going to explain maybe some of the data structures that are in there. Okay. So if you can stop this video and type in this code, or you can use some of this is in CodeCalc already, so just shift enter. So it's bringing in hopefully all the stuff that we need. We're going to bring in this headers data. And you can kind of see what it is, and you copy paste this and put it down here. We took out salary, and then we're getting the dummies. We're using this salary that is the logarithm of the salary. So this small s, and you got the big S right here. So it's 475. The logarithm of that, the log of that is the 6.14, and so on and so forth. So this is the logarithm of that that field right there. So I'm going to try to predict this because that's what the book does. Let's find X train, X test. So this first sort of column right here is basically just choosing the columns that we're going to use. It's getting the dummy variables because we got some qualitative variables in there. We're using that for my Y, the salary, the logarithm of the salary for my Y. And then we're going to break this up into train and test. And then I'm going to make one model, and I'm going to fit it and then predict it and then tell me what the answer is, right? So if you do all that, we get a model that's 61%. So I want a worse model, so I'm going to hit shift enter on 2, and so I was just going to keep going until I got something in the 50s maybe. So this is not a great model. The the R squared here is like 56%. So obviously that's not a great model. And now what we're going to do is choose 1,000. I mean, we could change this to 500 if we wanted to, whatever, but we're going to choose 1,000, and then we're going to, yeah, I don't need this. I don't need bag data. I don't think I ever use bag data, but we're going to use this bag model. And what we're doing is we're stepping through. So let's look at what this does first. IDX. So what does that do? So if you come back over to here, IDX is index. And all it's doing is it's creating this vector that's going from 0, 1, 2, ... Let's see how many we have in here. I forget how many. Let's go back. Hit shift enter. Let's go IDX. So IDX is this vector from 0 to 196. So that's all that is a vector from 196. And then I create this IDX underscore matrix. And then what does it look like? Well, it's a whole bunch of indices where each row represents a a bootstrap of IDX. So in other words, this first row here is an IDX bootstrap. Now, why did I need to do it like this? Because I need to, so if I were to put like a 2 here, and then 7, and then maybe 3, this is the index into the X values and the Y values because they have to match up. In other words, if I had, my X train 2, I needed to match with Y train 2, right? So I need to be able to, so if 2 is what my first number is, I got to be able to take that and put it with the Y train 2 so that when I train my model, it's training on the right thing. And that's why I use indices in here. And each row is going to represent a different bootstrap sample. So then I got row 2 here. Oops, move that out of the way. So row 2 here is going to what I'm going to use to build the second model. So these are the indices to build the second model. And these are the ones that build the first model, index to build the first model. And so on and so forth, right? So now I'm going to have a whole bunch of matrices or bunch of rows here, and each one of them is going to be related to a model that we're going to build. Let's see, index matrix. So IDX matrix, just to show you what this thing looks like. So these are a bunch of indices for row 1, and we're going to use these to make a model. Actually, you can see right here, right? So it used xtrain.ilock IDX I. So when it came through the first time, it was 0. So it was this first. So those were the X values for that. So matter of fact, let me just show you what that looks like. Control C. Control E. And these are the X values for. So let me print that. No, let me do this. Let me print IDX matrix. Oh. Okay, so this is the IDX matrix. And then IDX matrix 0, these are the X values for all of these things, right? So 99, 155. Yeah, so that 99 is the 99th index into X train. So if I were to throw in X train, you can see the 99th one would be 209. I know it's kind of hard to follow there, but these are the indices for all of these data points. All right, so now what I want to do, or I've already done this. I've already built the model. So bag underscore model, I appended a whole bunch of models into that data structure, right? So it's just a list, and then I appended, hey, fit the 99th one, 99th X value to the 99th Y train value, then the 15th one, and so on and so forth. So let me see here. Let me X out of here. And then now what we want to do is we want to take each one of these models that are in bag model, and we want to then predict using X test. So the question is, well, what is Y hat going to look like? So let's talk about that just for a second. So what does Y hat look like? So I claim Y hat is a matrix as well. And what Y hat contains is each one of these rows is going to be all the predictions. So this is the predictions for model 1. So if that's the case, then we know the number of columns of Y hat needs to be, so the columns is the number of elements in X test. Oops. X test. So because each one of these columns represents a number that's coming out of X test. So that's going to be for the first one, and then the next one will be for the second one, and so on and so forth. But this is all for model 1. And then the next row will be all of the for model 2. So the predictions for model 2. All right, and then dot 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 all the way to the 1,000th one, right? Because there's 1,000 models. So this number of rows is going to be 1,000, and the number of columns is going to be however big X test is. So let's go back over and check it out. So you can see Y hat is MP zeros. The number of rows is length of bag model, or you could just put B, would be fine. It's got to be a tuple in there. So B by the length of link test, right? So the number of values there, and then what's going to happen is it's going to go in here. Again, we could put B. I don't like the way that looks. It's just too cumbersome. And then I'm going to do this 1,000 times, and I'm going to get Y hat. So that's ith row, all the columns is going to be equal to bag model, the ith bag model, right? Because up here I trained 1,000 of these things, and then I'm going to predict X test. So that will give us each row will be all of the values for X test. So let's add here X. So X test looks like it's going to be 66. So that's going to be the length of, that's going to be the number of columns. And then for each one of these rows, I'm going to have a prediction for this one. I'm going to have a prediction for that one. So each row, there'll be 1,000 predictions for 262. So let's see what happens. And then I will look at one. I want to look at one column because that's really what we're talking about. So column 0 and give me all the rows. So what this represents, no, that's row 0, sorry. What this represents is that's the prediction for the first model on 262. And that's the prediction on the first model for 115. And that's the prediction for this first model for 277, and so on and so forth. So this is all of the test data, but I want to do the other way around. I want to have all the rows in the 0th column, and this should be 1,000. There should be 1,000 different numbers, maybe not different, 1,000 numbers, because they could be the same, for my prediction on what 262 is. So given all of this data, there's 1,000 different models that predict what number it should come out of here. So what we're going to end up doing is taking the average of each one of those. So shift enter, and you can see that I'm already giving you the scores is 70%. And we'll just do this as well. You can see 564 is the Y hat, which is the average of all of these numbers in here, and the true value is 5.252. And then if I were to show you the second column, oh, I already redid that. Hold on, let's do this. Shift enter, and then that's all the. I didn't need to redo that, but these are all. That's all the second column, right? Because it's the 1th column. And then if you go in here, you'll see 6.959. So this is the average of those, and you can see what the true value was, and you see what the difference is. Okay, so that's what I wanted to show for this lesson, is just to understand that bagging is trying to take out some of that variance of building one particular model. So there's a lot of variance in just doing one, but the idea is that we're going to now do a bunch of them and then use the ensemble method. That's what this taking the or using this mean of each one of these suckers. That's taking into account every single one of the predictions and putting them together into one, and then using that one instead of just one particular model. Okay, that's all I got. Hope you guys got something out of this, and see you next time.